We are going to look at density in this video. And I'm sure you've seen a picture like this or have seen, you've done this in real life where we are looking at substances that don't mix. So they form layers upon density. So we're going to find out later in this class what happens when do mix, right? So alcohol and water, they have different densities, and so we don't see those layers. But corn syrup and water, or this adding oil to it, they don't mix. They form layers based on their densities. So we are going to look at that, later in class. Right now, we're just looking at how things form layers based on a density difference. In this demonstration, we see a dense liquid at the bottom, a lighter liquid here, and then at the top, it looks like we have an oil. So we see some solid items that are floating in the different levels. So we know that the least dense thing is on top, and then the most dense thing is on the bottom. And we know this intuitively, right? Like you go to take a boat out in the water and you throw an anchor overboard, it's heavy, it's really dense. And that's going to sink. And you're not going to throw a piece of styrofoam out to anchor your boat, right? Because it is not dense. It's going to float on top of the water. So what is density? We're going to calculate density doing some different calculations, but we're also going to right now just look at the concept of density and the trends of density in this little video. All right, let's watch this experiment here. We've got a glass of water. We put in some water, some food coloring, and mixed it up. Now they're pouring in some very viscous corn syrup or honey. Added a little bit more water to that to give us about the same equal number of layers. And notice that this is some oil. Doesn't matter, sunflower oil, olive oil, canola oil. And it rose to the top. So we see very clear layers here. They don't mix. They have different densities and are not mixing. Now we're going to add in some objects into these layers. First we have a bolt. And notice that it goes right to the bottom. It is the most dense. And then we have a grape, which is about the same size as that bolt. But notice that, and I'm going to pause this right here, the grape stops right here. So it doesn't float on top of the water, but it doesn't sink to the bottom of that oil. It's about the same size, but there's less particles that are squeezed into that grape. So even though it's the same size, there's less particles in that grape. So it is less, it's less dense. It is, we'll say floating, but it is more dense than the water, but less dense than the oil. And let's see what we've got next. We've got this cap, again, about the same size. It's more dense than the oil, but it's less dense than the water. And then finally, we have this foam. Again, same size. Its mass in that same amount of volume area is less. Now let's go back to this image again, but really think about what is happening to the particles and the things that we can't see. But imagine the things that help us understand the concept of chemistry. So, like we said, all of these things are about the same size. So, about the same size as in the same volume. So, I kind of depicted these with the same size squares. Now, we said that this one was more dense. The particles, there are more particles and they're arranged tighter. So I depicted that by kind of showing that we've got, let's just say here, 1, 2, 3, 4, 8, 12, 16. We've got 16 particles in this box, as opposed to the grape, which is less dense, because let's say they've only got 12 particles in that same amount of volume. And then we have our cap here, let's say less particles still, so it's less massive. Not only is it less dense, but it's less massive for about that same size. So we've got a smaller number of particles and then our piece of foam, again, about the same size, even less particles. So less mass over the same amount of volume is going to give us something that's even less dense than the other three objects. So this just kind of gives you a conceptual understanding of those four pieces. Now, let's think about the three liquids that are here. We've got our viscous corn syrup, we have our dyed water, and we have our oil here. Because the bolt is the most dense, it is sunk, so it is more dense than the corn syrup. So the corn syrup must be less dense. Again, these three liquids are about the same volume. So the difference between these three liquids, again, in that same amount of space, we have the water has less particles for the same amount of volume than the corn syrup does. And if I looked at the bolt versus the corn syrup, we can see in that bolt has more particles per volume. So it is more dense than the corn syrup. The grape compared to the water, we can see that there are less particles, right? That grape is more dense than the water. There are more particles, more mass for that same amount of volume than the water has. We can see the water, let's say we've got 3, 6, 9, 10 particles in that volume versus this has 12 particles per volume. So that grape is more dense. So hopefully that has helped you to kind of conceptually understand what's happening here. Density is mass divided by volume. And in this case, what I kind of showed you visually, even though we can't see these particles, is that we're able to take the number of particles and divide it by the shape. So if I were to compare the mass of my oil here, if I did 1, 2, 3, 4, 5, 6, 7, 7 divided by my shape, my square, whatever the area is, compared to my foam, 1, 2, 3, 4, 5, 6. 6 divided by that area. Let's say the area was 1 times 1 times 1, so the volume would be 1. So 1, 2, 3, 4, 5, 6, 7 divided by 1 versus 6 divided by 1. This is less dense. Let's say that I wanted to compare the density of this object versus this object. We would say, well, we have again, the number of particles per volume or per the shape. So 1, 2, 3, 4, 8, 12 compared to 4, 8, 12, 16. Well, this one is more dense. There's more particles in a given amount of space. So more dense, less dense. But let's say that I had this guy in a larger space. Which one of these would be more dense? Well, these are going to expand, right? Or let's just say that I've got 1, 2, 4, 8, 12 particles, and let's say this is double the size. So 2 times 2 times 2, length times width times height would give us our volume. So 2 times 2 is 4 times 2 is 8. So I've got 12 divided by 8 versus 12 divided by 1. This is going to be more dense than this one. It will be less dense. That will give me a smaller number. There are less particles in a certain area. Once that denominator, that shape, that volume becomes bigger, then our density becomes smaller. This is a fun simulation to kind of practice what we've been learning and calculate the density of these different objects. If you take these objects and let's say I put it onto the scale to get its mass, 2.5 grams. And then to get its volume, notice that my starting point here is 25.5 milliliters. So when I take this and I pull it all the way underwater, it goes to 29.6 milliliters. I'm going to subtract the difference in those two. So 29.6 minus 25.5, and I'm going to get 4.1 milliliters. as my volume. So to find the density, I'm going to do 2.5, which is my mass, divided by my volume. And again, we said that as 4.1. And I would get a density of 0.61 grams per milliliter. 0.61 is smaller than the density of this liquid, which is 2.5, so therefore it floats. Now let's check out gold, for example. Let's say I have a piece of gold. Notice that this object sinks. Let's find out what its density is. I'm going to put it on the scale, and we get 40.53 grams. And again, my starting volume is 25.5. So to find the volume of the lead, we do 27.6 minus 25.5, and I get a 2.1 milliliters. So we're going to do our mass divided by volume. So 40.53 divided by 2.1, and we get a density of 19.3. That is greater than the density of the liquid, so it will sink. You can do the same thing for the iron, the lead, the wood. And again, if something is sinking, that means that there are more particles in a given volume than something like wood that is going to float. And so you could take and measure the mass of this, 1.95 grams, divided by the difference of 28.5, that would be 3 milliliters. So 1.95 divided by 3, and that would give us 1.95 divided by 3. Again, about 6.6, meaning it will float. So I will put the link to this so you can do some more practicing. And you can also change the density of your liquid to figure out what the density of this object is. And then how does that change whether it floats or sinks depending on the density of the liquid. So I'll put that link right underneath of this video, and have fun exploring. Continuing on with looking at density, mass, volume, and all of that, we were talking about volume displacement, and we were taking that, for example, that piece of wood and pulling it down underneath of the top of the water since it floated. But we can calculate the volume of a solid by looking at that water displacement. And over here to the right, we can see that we have an initial volume of 50.0 milliliters. And then I put in this green jade sample and the water rose to 60.5 milliliters. So we can find that difference by simply subtracting those two. So 60.5 minus 50.0. And we can see that this is going to be 5 minus 0 is 5, and 60 minus 50 is 10. And we know that when we are subtracting or adding, we are significant to the placeholder that they have in common. So in this case, it would be to the 10th. So we would say that that volume is 10.5 milliliters. We can also do the same thing by finding the volume of a gas by displacement. So for example, here I have a sample of gas, and we heated it. So that gas, those particles are going to expand and go into this vessel, and therefore the gas is going to take up space and it will push the water out. So we can see how much space that takes up by how much water is expelled and pushed out. Here's another example where I have a starting volume, and in this case it would be really important, especially if you were in lab and looking at the initial volume of this, we want to look at what our units are. So we can see that this is 10 and this is 15. So each of these small little tick marks must be 1 milliliters. So 10, 11, 12, 13, 14, 15. Yep, each one are 1 milliliter. So therefore, since this water is in between this tick mark and that tick mark, I would need to estimate to the tenths where that water line is. So it's not 13, it's not 14, so they said that that initial reading was 13.5. You might have said 13.4. Then we put in this rebar, and we can see that it went from that all the way up to, this is 20, 21, 22, somewhere between 22 and 23. So we have to estimate to that tenths. They estimated it was 22.4. You might have said 22.3 or 22.5. We know that that tenths digit is going to be an estimated digit. Okay, so we're going to find the overall volume of that rebar mass by final minus initial. So 22.4 minus 13.5. So we have 0.9, and then 8.9 milliliters would be my volume. I'm given the mass, and we know that we can find density is mass divided by volume. We can use this cute little handy dandy helper. So we cover up what we want to find. If this is what I want to find, then it's mass over volume. So I would take my 69.658 grams divided by my change in volume, so that 8.9 milliliters. And we know that when we divide, I have to look at the number of significant figures. So I have 1, 2, 3, 4, 5 sig figs on top and 2 sig figs on the bottom. So I'm going to finish with 2 significant figures. My calculator gives me an answer of 7.8267. And again, I only want 2, so I'm going to finish with 7.8. In my units, it's going to be the mass, which is in grams, divided by the volume in milliliters. So 7.8 grams per milliliter. Here's one I would like for you to try. We are given the mass of this, it appears to be a gold nugget. See if you can find the volume of this gold nugget and press pause. We'll come back and figure this out together. All right, let's look at this. Our initial volume in our graduated cylinder, we can see that it is a little bit more than 17, not much. So I wrote down 17.1. You might have said 17.2, 17.3. That's okay. Remember, that tenths is an estimated digit. Then, after we put the gold nugget in, it looks like it's almost to 20, but not quite to 20. So here we've got written down 19.8. If you have 19.7, if you had 19.9, those are all okay. So to find my change in volume, we just simply need to subtract final minus initial. Oop, I guess I don't need to do that. 8 minus 1 is 7. 9 minus 7 is 2. So 2.7 milliliters is my change in volume. So then density is mass divided by volume. So 51.842 grams divided by 2.7 milliliters. Now my calculator told me it was 19.2 grams per milliliter. Am I done? Well, I need to look at significant figures. I have 1, 2, 3, 4, 5 sig figs on top and 2 sig figs on the bottom. So I'm limited to 2. That means I got to look at my answer, and right now I have 3. So I need to go 1, 2. What does that 2 do to the 9? Nothing. It's going to be 19 grams per milliliter will be my density. Now sometimes we need to find volume not just by looking at a graduated cylinder. We might have to calculate it. And if it's an object that is, let's say, a rectangle, I need to do length times width times height to find the volume. And all of these measurements need to be in the same unit. So if this is inches, if one is in inches and one is in meters, you need to get them all to the same unit, so it might require some unit conversions. So let's say if I had an object and it was 3 centimeters by 2 centimeters by 1, I'm just going to do 3 times 2 times 1, so 3 times 2 is 6, times 1 is still 6. And then I have to look at those units. Centimeters times centimeters times centimeters is centimeters cubed. And that means cm3 is cubic centimeters. Here's an example. If I had a stainless steel rectangular container, and I know its length, its width, and its height, length, width, and thickness, whatever. Let's find the volume. So I'm going to do length times width times height, and this is what I get. Is that correct? Nope. What's wrong with it? Well, I've got 3 sig figs times 3 sig figs times 3 sig figs. I need to end with 3. So I'm just going to go 1, 2, 3, draw a line after my third. Will that 2 change the 8? No. 46.8 cubic centimeters. Here are 2 I'd like you to pause the video to try and work through. If I have a rectangle solid with a length of 25.0 millimeters, a width of 10.0 millimeters, and we know the volume is 3.75 cubic millimeters, what's its thickness? And find the volume of an object if I know the volume of the object and water, and the volume of the water. Pause, then come back in to check in. All right, let's look at this first one. I set it up. We know the volume is length times width times height, or length times width times thickness. We were told the volume was 3.75, so I just plugged that in on the left. We were given length, we were given width. So to find this thickness, I combined 25 times 10 to get 250. So 250t is equal to 3.75, divided both sides by what my t was attached to. And my calculator spit out that I had 0.015. And I almost left it there. But I went, okay, how many sig figs do I need in my answer? I have 3 here, I have 3 there, and 3 there, so I need 3 in my final answer. If I look at this, this is only 2 sig figs. Remember, the 0 to the left of the number don't count as being significant. So I needed to add a 0 to the right of there to give me 3 sig figs. A 0 that's to the right of a number and right of a decimal is considered significant. All right, this next one, okay, I was given my volume of the object and water and the volume of just the water. So we know that to find the volume of the object is VF minus VI, so 48.6 minus 42.1. And I got 6.5 milliliters for the volume of my object. If I were to look at significant figures, it might be easy, just like we did up there, to go, well, I had 3 there and 3 there, so I need 3 for my final. But remember, I'm subtracting here, so we have to look at placeholders. They both have the tenths in common, so I just need to finish with the tenths place. Okay, let's put it all together. If we look at density, we've talked about, that means we're looking at the concentration of mass. Okay, so the more concentrated the mass is in a certain volume of sample, the greater its density. Density is defined as the amount of mass per unit volume. So density is mass divided by volume. And I showed you this earlier, but I really like to also show it. Density is mass divided by volume. So you can cover up, if I wanted to find mass, for example, cross that out, mass is equal to density times volume. See how they're next to each other? That means density times volume. If they're next to each other, that's multiplying. Or if I wanted to find volume, cover up volume, volume is m over d, so mass divided by density. Now, let's look at these. I'm given the mass of 4 different substances here: ice, water, lead, and osmium. And I'm given the volume of all 4 of these. So we could find the density of all of these, mass divided by volume, for each one of them. Now it says if we have a platinum nugget that has a mass of 214.50 grams and a volume of 10 cubic centimeters, what is the density of that metal? Okay, we just need to do mass divided by volume. 214.50 grams divided by 10.0 cm3, so grams per cubic centimeter will be my units. And I should get 21.45, my calculator would spit out. But again, I want to look at how many significant figures. I'm limited to 3 significant figures, so that 21.45 would round up to 21.5. And if I were to ask you which one of these is the most dense, the ice, water, lead, or osmium, if I did mass divided by volume, and each one of these was divided by 1, obviously this would have the greatest number. It'd be 21.5 grams per cubic centimeter. That means this has the most mass, the most concentrated mass in a sample comparatively to all of these. So this is going to be the greatest density. It will sink if it's in water. And we have ice here. 0.917 divided by 1 would give me 0.917 grams per cubic centimeter. It would have the smallest density. It would float in water because water's density is 1. Why don't we look at this next example? What's the volume of a platinum nugget that has a mass of 224.50 grams and a density of 36.2 grams per cubic centimeter? Pause the video, write down what you know and how to get volume. All right, and again, if I want to find volume, it's mass divided by density. So I took my mass divided by my density, and again, I needed 3 significant figures for my final answer. So 6.20 grams per cubic centimeter. And similar to what we saw at the very beginning of this video with the simulation and me showing you a picture like this with all of the particles and their arrangements, looking at different densities, we can look at the density of one substance compared to another substance and estimate its density by seeing if it's floating on top of a liquid. We know that it has, like S1 has a smaller density than S2, and S1 has a smaller density than water, but it has a greater density than L1. So we can look at the arrangement of particles and be able to compare the density of one object or liquid comparatively to others, depending on if it's sinking or floating.